Okay, so using properties of exponents. Properties of exponents, let's just zip through these real quick. Now, in these examples, notice that it's telling us here that A and B are going to be real numbers, any kind of real number. Could be fractions, could be square roots, could be pi, could be anything. M and N are integers. Could be negative, but they're going to be, -5, -3, +7, 0, +1,000. Got to be integers. Okay, what do we know about this? The product property. What this is telling us here is that if I multiply a to the m times a to the n, so the bases are the same, what do I do to the exponents? When I multiply like bases, I add the exponents. Good. So, for example, if I have x cubed times x squared, that equals x to the fifth, because I'm multiplying like bases. What if I multiply x cubed times y squared? Yeah, that's it. I can't combine those because they're not like bases. Okay? What if I multiply 2x cubed times x squared? Yeah, so 2x to the fifth, right? Because the 2 I can't combine with the x's, but the x's I can pull together. Okay, make sense? Okay. Okay, next, the power of a power property. I don't care a bit if you remember what these things are called. It makes no difference. Just know what they mean and how to use them. This one says if I take a power to a power, I, multiply the exponents. Okay, so for example, if I have x cubed squared, that equals x to the sixth. Good. Take power to power, you multiply the exponents. Okay. Power of product property. Okay, now this one we gotta be careful on this a little bit. If I take the power of a product, so in other words, I've got a product of two or more factors in parentheses that are all being taken to a common power. What this tells me is in that case, I can distribute the exponent to all of the factors. So for example, what if I've got x squared y cubed to the fourth? What does that equal to? Okay, good. Make sense? Okay. What if I have 2x squared cubed? Okay, 2 cubed, x to the sixth. What is 2 cubed? 8. Okay, 2 cubed, which is 8, x to the 2 times 3. We distribute, and all I'm doing in each of these cases is distributing that power, right? Okay, one more while we're at it. Here's the dangerous one. What if I've got 2 plus x squared cubed? Okay, no. It is not equal to 2 cubed plus x to the sixth. It's much harder than that. What it is equal to is 2 plus x squared times 2 plus x squared times 2 plus x squared, which is an enormous mess. I boil that out 2 at a time. Now I'm going to show you, this chapter will come up with a shortcut formula for dealing with expansions like this. But there's a lot to it. It's not easy. I mean, it's going to take us a whole day to talk about it. It's much harder to do something like this than like this. If I'm taking a power of a product, that's easy. A power of a sum or a difference, it's hard. Okay, that's good. That's harder to do. So the red flag there is because these are being added, or if they were subtracted, that means I can't do that. You can only do that when they're being multiplied. Okay, make sense? So be careful with that one. It's an easy one to mistake. Negative exponent property. Now we're going to add to this a little bit. This just says that a to the negative m. So if I have a negative exponent, what can I do with that? It becomes positive where? On the bottom of the fraction, in the denominator. Okay, but this works both ways. What we're doing with this negative exponent property is we're comparing behavior in the numerator to behavior in the denominator of the fraction. And what we can say about it is this. We can improve this one to say a to the negative m equals 1 over a to the m, but also 1 over a to the negative n equals what? I'm seeing it in the back there. A to the positive n. So here's how you remember that. A negative exponent in one part of the fraction, meaning numerator or denominator, always means a positive exponent in the other part of the fraction. So a negative exponent in the bottom is positive on top. Negative on top is positive on the bottom. Okay, it works both ways. Okay? The zero exponent property tells us that any base taken to the 0 power is always 1, by definition. So what's this one? One. It doesn't matter how ugly the base is. If this whole thing is being taken to the 0 power, it's 1 every time. Okay? Quotient of powers. Now this one goes right along with the product of powers. Right there. Power of product. Okay. Oh, no, it doesn't. Sorry, wrong one. Whoops. Goes with now. Okay. What it says is that just like if I multiply like bases, I add the exponents. If I divide like bases, I subtract the exponents. And all it really is this property. It's the first property we talked about, the product property plus the negative exponent property. I'll prove it to you. Okay, what if we want to, so we'll come up with this formula really easily. A to the m over a to the n. Now, a positive exponent on the bottom, we said, correlates with what? Corresponds to what on the top?
Negative.
Negative on the top. So isn't this the same thing as a to the m times a to the negative n?
Mm-hmm.
And then if I multiply like bases, I add the exponents. Well, those are like bases that are being multiplied. So that should equal a to the m plus negative n, which is the same thing as a to the m minus n. Right? Yeah. Okay. So that's an easy way to get that result. But it's, once again, not a complete picture. We really want to say this in two different ways. Rather than the way the book says it, it's better to think of it this way. A to the m over n is equal to, true, it equals a to the m minus n, but it's also equal to 1 over a to the n minus m. Now, why would we ever do that? Here's an example of why we would, exactly why we would do that. What if I gave you the problem x cubed over x to the 7th? Okay, now, according to the book and the PowerPoint and all that stuff, what I would have to do is write that as x to the 3 minus 7, which is x to the minus 4, and then what do I do with the negative exponent on top? Put it on the bottom. Well, look how much easier it is if I just do this. if instead, when we're doing a quotient of powers like this, or we're doing a dividing like basis, we ask ourselves, where is the biggest power of the base, top or bottom? Bottom. So we're going to keep the base where it has the most power. So we'll keep it in the bottom, the one on the top, and then we'll subtract the other exponent from that one and just keep it put. So we've got x on the bottom to the 7 minus 3, which takes us straight to the answer, 1 over x to the 4th. Okay? Right? So the rule is, keep the base where it has the most power and subtract the other exponent from it. Make sense? Okay? And then I think this is the last one. Power of quotients. And all this says is, if I'm taking a quotient to a power, then I can distribute the power over the quotient just like I could with the product. And here's an example of that. Okay, what would you do? In fact, we'll combine both of those properties together. What if I had 2x squared over y cubed cubed? Good. I can take this power and I can distribute it to all of the factors on the top and the bottom. So it's going to go there, there, and there. And I get 2 cubed, which is 8, x to the 6th over y to the 9th. Okay, what about this one? What if I have 2 minus x squared over y cubed squared?
Oh, the X was on the bottom.
The same thing.
So I can't distribute on the top, can I? Can't do that because these two terms are being subtracted, right? So on the top, I'm stuck with 2 minus x squared squared, which I can expand out if I want to, but I can't distribute. To expand that out, I have to FOIL it out, right? Now on the bottom, what could I do? On the bottom, I can't, because the bottom's only got 1/5. Make sense?
Yeah.
All right. So real quick, take a look at that. What do I get? -5 to the 9th. Multiply like basis, you add the exponents. Okay, and if I do that, it's just some big negative number. Okay. Notice that a negative number to an odd power is negative. When I multiply those together, negatives times negatives make positives, right? But if I have an odd number of 5s being multiplied together, I'm going to have pairs of 2s and 1 oddball left over, right? If I have 9. I'd have 4 pairs of 2 and 1 left over to make the overall sign negative. Does that make sense? Okay? What's that? Good. Multiply like basis, add the exponents, x to the 7th. Variables are easier than numbers, aren't they? I mean, that's it. You're done. It didn't used to be that way, but now in algebra, we're tipping over to a point where we actually like variables better than numbers. They're cleaner. What about this? 2 to the 12th. Second B. How can I figure it out? 2, you'll know these pretty quick. 2 to the 1 is 2, 4, 8, 16, 32. 2 to the 6th is 64. Right? So if I wanted to figure this out, what 2 to the 12th was, I could, right, very good. I could say this, couldn't I? I could say that's the same thing as 2 to the 6th squared, because a power to a power multiplies to 12. I can reverse that, right? So that's the same thing as 64 squared. So that'd be easier to do. We could even do that in our head if we wanted to think about it. 64 times 64. But it'd be pretty hard to do otherwise if I had to keep going through that list up to 12. Okay? Okay, and so it's big, 4096. Okay. What about this? 3 to the 8th, that's big. Okay. What about that? -5 to the, -2. Good, I'm going to add those up. So I can do something else with that. Okay, yeah, that goes on the bottom, doesn't it? So 1/25. If I square, in fact, if I take a negative number to any even power, I get a positive result. So what's our rule when we're actually doing a computation like that? If I take a negative number to an even power, put in the positive number instead. So you don't make the mistake of not putting the negative number in parentheses. You know the answer needs to be positive, so just put in a positive. Okay, what about that? Yeah, good. You divide like basis, subtract the exponents. 5 is bigger than 3, so we'll keep that on the top. Right? Keep the exponent on the top. Okay, what about this? Distribute the power. So r squared over s to the -10. Now what? Yeah, good. Negative exponent on the bottom, positive on the top. Okay? Good. What about this? Bunch of ways we could go about this. What are some things we have to do here? Okay, we distribute the 2. Okay, I got all these like bases. Now I'm going to end up with 7 squared is 49. I've got b to the -6 times b to the 5 times b to the, what? 1. So those are all just going to add up. B to the -6 plus 5 plus 1, right? Which is just b to the 0. What's that? 1. Anything to the 0 is 1, so the answer is 49. Okay. Okay, what about this one? They're going to do this one wrong. We'll do this one better than that. How do we do this one?
1 over x.
Good. 10 is bigger than 5. So we'll keep the base on the bottom to the 10 minus 5. Right? So we get it really in one step. They do this. They do it backwards. Okay, scientific notation, no big deal. Scientific notation has some, there really is a benefit to this. If we want to take this enormous number and write it in a smaller way, what we do is we'll look at one example of this now, and we'll look at an example where we go to the other direction later. But for now, we'll look at a big number. The decimal starts there, right? The number of shifts of the decimal that I have to make to end up with a base number that is greater than or equal to 1. So 1 would be okay, 1.2 would be okay, 0.9 wouldn't. So greater than or equal to 1 and less than 10. Tell me when to stop with the decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Stop right there, right? 1.31 fits the bill. That's greater than or equal to 1 and less than 10. So was that 11? 9, yeah, 11. So then that would equal, because I moved it 11 places, I'm going to have 1.314 times 10 to the 11. The number of shifts determines the power of 10 in the scientific notation expression. There it is. Okay? Yeah. Okay. So what about this? What if I want to divide those two using scientific notation? Well, I could turn them both into scientific notation numbers. Top one we already did. Bottom one I would only have to shift it 1, 2, 3, 4, 5, 6, right? So 5.284 times 10 to the 6. And then I can break this up. I've got this times this divided by this times this. Well, I can break that up into 2 separate quotients that are easier to manage. 1.314 divided by 5.284 I could get. And here's the thing about this. What if I were doing what we call a shirt sleeve calculation? I didn't need to get an exact answer. I just wanted to ballpark it. If I wanted to ballpark it, well, that's something I could do pretty easily. 1.3 divided by 5.2. I can get a pretty good estimate of that just in my head. Doesn't have to be that exact even, right? And then this is easy. We get an exact answer for that one. 1.3 over 5.2 ends up being what? 2.49. So, and we could have estimated that. That is 1.3 times 2 is 2.6 times 2 is 5.2. I mean, that is, if you ignore this stuff right here, that is 1/4, right? So we could have easily said, yeah, that's about 0.25. So 0.25 times 10 to the, well, look here. Divide like basis, subtract the exponents. So 0.25 times 10 to the 5th, I would just have to, if I want to turn this into a regular number, I'll move the decimal to the right that many places, right? So I'd end up with 24,900. So you see, I'd be able to do that then. This is pretty daunting to try to do that in your head, all those zeros. I mean, we wouldn't want to try that. But this wasn't so bad, right? Get the idea? Okay. All right, I think that's it. Yeah, let's go to the lab. How about?